The next time you look down at your wrist to check a fitness route or pull up a map on your phone, think about how that device actually pinpoints your location. That mundane, everyday action relies entirely on a massive, invisible infrastructure of hardware, silently orbiting tens of thousands of kilometers above your head. But if we wind the clock backward, erasing that digital web year by year until we hit the mid-20th century, the space around our planet goes completely, eerily quiet. To understand how we wove this modern, synchronized net of data around the globe, we have to trace its evolution all the way back to a single, primitive ancestor. The silence officially broke on October 4, 1957, when the Soviet Union launched Sputnik 1. By modern standards, its construction was incredibly limited. It was a polished aluminum sphere roughly 58 centimeters across, weighing just over 80 kilos, with 4 long antennas trailing behind it. It had no cameras and no onboard computer. Its sole function was to transmit a continuous radio pulse, a simple bip-bip tone, so scientists on the ground could study the density of the upper atmosphere. Orbiting high above the surface, this small metal ball completed a full revolution around the Earth every 98 minutes. While primitive, Sputnik successfully proved the practical physics of artificial orbit, serving as the foundational building block for all the space engineering that followed. Once that baseline was set, the 1950s and 60s saw rapid acceleration in engineering as scientists stacked new capabilities onto that initial concept. In 1958, the SCORE satellite managed to transmit the very first spoken human voice from space back to the ground. By 1962, we launched Telstar-1, a machine covered in square solar cells that relayed the first live television signals across the Atlantic Ocean. This diagram illustrates the orbital mechanics required to keep these heavy machines from falling back down. Engineers have to perfectly balance two opposing forces: a satellite's extreme forward speed, often exceeding 40,000 kilometers per hour, and the inward-downward pull of Earth's gravity. But to maintain a permanent, live communication link, you need a satellite to stay in one exact spot relative to the ground. This requires a specific trajectory called a geostationary orbit, where a satellite is placed at a much higher altitude, so its orbital speed perfectly matches the rotation of the Earth. In 1964, a satellite named SYNCOM-3 successfully locked into this exact orbit, enabling unbroken, live transmissions for the very first time. Mastering both the raw payload capacity to lift these instruments and the precise orbital mechanics to position them allowed humanity to build permanent communication bridges in the sky. Today, that early analog engineering has fractured into highly specialized digital forms operating at extreme physical scales. At the upper extreme, scientific giants like the Hubble Space Telescope stretch 13.2 meters in length and weigh a massive 11 tons. On the opposite end of the spectrum, we see hyper-miniaturization, most notably with a class of tiny devices known as CubeSats. These miniature satellites are roughly the size of a standard shoebox. By drastically reducing the physical footprint, they have aggressively lowered spaceflight costs and democratized who gets to put hardware into orbit. Between those extremes sits the highly specialized navigational network of GPS satellites, the exact machines actively plotting the maps on your personal devices right now. In the span of a single human lifetime, that solitary, beeping sphere of aluminum became an invisible, hyper-capable network of data that silently operates modern civilization from the vacuum of space.